Everyone we look at is the motion of point particles or charged particles in electric fields. So what do charged particles do when they interact with an electric field? Well, positive charges we know feel a force in the direction of the field, and negative charges feel an equal and opposite force against that field. So here's our question. Example 1, we've got a nice steady electric field here. We've got an electron that is fired with an initial velocity into this field. We want to know how far does it travel. So here we go. We got the electric field strength of 1,000 newtons per coulomb pointing from the left to the right, and we've got the initial velocity of the electron at 2 times 10 to the 6th meters per second. That's 2 million meters per second. And yes, that is street legal. The fastest things can travel is the speed of light, and even things with mass can't reach that speed. So as long as they stay under the speed of light, you know your answers are good, or at least the given information in the beginning makes sense. So what's this charged particle going to do? Well, we have an electric field pointing from left to right, meaning that over here there must be some large positive charge, and over here there must be some large negative charge, just because of the direction of the field. So that tells me right off the bat that this charged particle is going to feel a force backwards. That force is going to decelerate the electron. So the electron's going to go over, it's going to lose velocity, come to a stop, and then it's actually going to start returning back to its origin point. I want to know how far does it travel just to get to the stopping point. So I know that my VF is going to be 0. There's no final speed. I know my starting speed. I need one more piece of information to go back to good old-fashioned kinematics to solve for how far. When we do this, you want to remember that electric field strength is defined as the force per unit charge that is in that field. So knowing the electric field strength, I could solve for the acceleration by swapping out F to make that mass times acceleration. And if I want the acceleration of my charge, I can rearrange to give me this. The acceleration of the charge is going to be Q over M, the charge per mass ratio for the electron, and we're going to multiply that by the electric field strength. Taking a look at units there, that's going to be coulombs per kilogram, and electric fields are newtons per coulomb. So you can see my coulombs are going to go away. The newton divided by a kilogram, remember a newton has some hidden units to it. A newton technically is a kilogram meter per second squared. So yes, you will get an acceleration in the end. Putting in the information you know, the charge of an electron, the mass of an electron, and my electric field strength, I calculate this acceleration, 1.76 times 10 to the 14th meters per second squared. And it's a deceleration, so it's backwards trying to halt the electron. Knowing this, I want to just find distance. If I want to find distance here, going down the list, I have the final velocity, I have the starting velocity, and I have the acceleration, so I can use my kinematics equations to solve for distance. When you do that, you find out that the electron made it 0.01137 meters. So it didn't make it that far whatsoever. It made it a whole 1.137 centimeters. So it didn't go far at all before it quickly came to stop, going 2 million meters per second to 0 in 1 centimeter. That's some big braking for that electron. And if you wanted to solve for time, if you were curious about how long that took, so if you solve for the time there, the time for that charge to stop in 1 centimeter is about 0.11 nanoseconds. It's a very, very quick time for it to stop. Again, any normal mass wouldn't be able to handle it, but the electron has such a small mass that it's okay to experience such a high acceleration. But what about this? Now we have an electron and the field is down. So when the field is down, that charge is moving across the field. And this heading here says this is projectile motion with an electron. What that means is that when this charge moves through the field, the electron goes against the electric field and is going to feel a force upwards. It's trying to move forward. Technically, it will follow this curve. And every moment that it's in the electric field, the horizontal velocity is going to remain constant, and the vertical velocity is going to grow and grow as this thing accelerates. So it's kind of a reverse of a projectile. Instead of arcing down towards the ground, this one's arcing up. And we can do all the things we did in projectile kinematics. In the horizontal direction, we know the initial speed is also equal to the final speed, since the velocity is constant. The displacement is just how far you travel in the x direction. The acceleration in the x direction is 0, and it's going to take some time to pass from one side to the other. Vertically, in that y direction, the initial velocity we could say is 0. It hasn't moved up or down yet as it's entering this field. The final velocity is an unknown. But the acceleration, when we did projectiles, the acceleration was just caused by gravity. But now our acceleration is that q divided by m times the electric field. And this works in nice, steady electric fields. If you had an electric field from a point charge, the charge would accelerate away or towards that point charge. However, the electric field strength would be changing with distance, so you'd have to integrate. Most of the times for this section, what we're going to do is deal with charges accelerating in nice, constant electric fields. We could also figure out the distance it was deflected in the vertical direction, up or down, and the time it takes it to do that. Just like before, if you solve for time in the x or the y, you can substitute the time into either direction. We can do projectile motion for electrons now, or protons. Any charge that enters the field will start to curve if it's crossing the field perpendicularly. If it's moving with the field, then it's going to accelerate or decelerate depending on the charge and what it was doing at first. So this is what's happening inside the old cathode ray tubes TVs or in some printers. What they do is they charge the toner or the ink. The charge goes through a deflector plate, which means it turns on an electric field, and that charged particle will be deflected up or down depending on how far it needs to go. If it needs to go on a very, very steep curve, you can have a very, very strong electric field, and if you need a very weak curve, then you use a small electric field. So how about this? The electrons launched with an initial velocity of 45 degrees. Question is, where does this electron go? Well, the electron goes against the electric field, so it's going to feel a force in the downwards direction, and it's moving up and to the right. And if that's the case, the vertical velocity is going to decrease while your horizontal velocity stays the same. So the electron is going to arc, and you can figure out exactly where it's going to arc and hit using good old-fashioned projectile kinematics. What if that charge was a positive instead of a negative? Well, if this was a positive proton, that would feel a force upwards. And feeling a force upwards would cause it to arc and hit the upper plate. So depending on which plate the charge hits, we could determine whether it was positive or negative. And this is the setup for J.J. Thomson's experiment for solving for what charges are actually moving in a beam of charge. What he did was he fired charges through a deflection plate. Charges went through the plate, and if they were positively charged, the charges would arc towards the top, and if the charges were negatively charged, they would arc towards the bottom. But when you do a problem like this, don't follow those first curves I just made. When a charge enters the deflection plates, it feels a force while it's in the electric field. So it will, if it's heading to the right, start to curve along its projectile path, but once it leaves that deflection plate, there's no longer any force on it. So once it leaves, it's now going to follow a nice steady speed until it hits that fluorescent screen. And this is what was going on in old big cathode ray tube televisions. In an old television, there were 3 electron guns. What I mean by electron guns is they actually accelerated electrons whether they were at the correct energy for red light, blue light, or green light, and they shot them through deflection plates. If the top corner needed to be blue, you use an electric field to deflect those charges into the correct orientation, where they needed to go on your screen. There's a little bit more work on the cathode ray tubes, But right now, electric fields can guide your charges from the back of the screen to the front of the screen. When those electrons energized hit the front screen, there was a fluorescent coating on the front. They would strike that coating, give off their energy, and fluoresce in whatever color strike that part of the screen. So if you needed a red shirt down the bottom corner, use an electric field to deflect the electron down to the bottom and allow the screen to glow red. Which leads us to electric dipoles. And what is an electric dipole? An electric dipole is a system of oppositely charged particles that are separated by some distance L. So the simplest dipole around is the hydrogen atom. It's a positive nucleus and a negative electron that's orbiting it. So they are separated by a slight distance d, and so there is this, what we call a dipole moment, that points from the negative charge to the positive charge. So we represent that, unfortunately, with the vector p, which looks a lot like momentum, but we're going to use this to represent our dipole moment. So p will equal q times the length of separation, and remember the dipole points from the negative to the positive. Water is a polar molecule because the way it sets up, there is a excess -2 charge on one half of the water molecule, and there is the 2 positive hydrogens on the other side of the water molecule. The water molecules look like Mickey Mouse, and if you look at the orientation from the negative charge to those 2 positives, water has a dipole moment. So we have polar molecules, or we have any dipole that has this dipole moment. When you place dipoles in an electric field, you can see that there's a negative charge down below and there's a positive charge above for this dipole. It has a dipole moment that's pointing up from the negative to the positive. And if you put it in an electric field, the positive feels a force to the right and the negative feels a force to the left. The dipole is going to try and orient itself with the electric field. The dipole is going to feel a torque. Since the dipole is going to feel a torque, there's a force acting at a distance L from the dipole. So you could say force cross L sine of theta. Now the electric force is coming from electric fields. So we could substitute electric force for electric field times charge. And we just highlighted that Q times L, that separation distance there, is our dipole moment. So another way to write the torque on a dipole is you could say that torque is the dipole moment crossed with the electric field. So if you take that dipole moment that is up and to the right, and if you take that force, which is all the way to the right, torquing those gives you a torque into the page, which is going to make this whole thing rotate clockwise. So the atom's going to orient itself and rotate clockwise. What happens when it spins too much and my dipole now looks like this? Well, when my dipole moment looks like this, do your P cross E, and when you do the dipole moment across the electric field, you're going to get a torque back in the opposite direction. So the polar molecule will try and spin back and forth until it moves and orients itself perfectly with the electric field. And if there's any frictional forces involved, then it can eventually lose that motion and stop. But what about the work done? Is a torque dot theta. So if I put my torque equation into my work equation, I get the dipole moment dotted with the electric field multiplied by the sine of theta d theta. So if I wanted to integrate and solve for the work would be my potential energy. That's where the negative comes from. I'm trying to decrease the potential energy of the dipole. So you're left with P dot E cosine of the angle between them. Solve for the potential energy, it's a dot product of the dipole moment and the electric field. The torques will cause the dipole to rotate and release energy and try and orient themselves with the electric field. So where is this useful? Why does this even matter? Well, molecules will be induced to become dipoles and create dipole moments just by polarization. Remember bringing the balloon next to the wall. the charges in the wall separated from positive to negative slightly. If there's a slight separation there, the molecules become dipoles. And if they become dipoles, you can then create torques on them and have them release some energy. So that's how charged particles move in electric fields. Independent point charge particles will either accelerate, decelerate, or follow projectile motion. And we can see if we have a dipole molecule in an electric field, it'll experience torques, start to spin, and decrease potential energy because of that rotation.